Oh.
Tanah.
Oke, Assalamualaikum warahmatullahi wabarakatuh. Selamat siang, good afternoon all. I hope we are all in a good health today. So today we are going to take part in the 7th series of the Trisakti Mining Webinar with the topic of PCBC and its application for block caving mining and geotechnical data management system. Our speaker today is Mr. Mathijs Mol, as mine engineer at CMOC Noerthparkes Mine NSW Australia. And also this webinar is moderated by Mr. Sandi Firmanullah as a mining professional. First of all, we will listen to the opening speech from our head of the mining engineering department Trisakti University, Bapak Dr. Insinyur Irfan Marwanza, STMT IPM. So Pak Irfan, please, sir.
Okay, thank you, Pak Yuga. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Welcome to the webinar for the PCBC and its application for block caving mining and geotechnical data management system. I'm Irfan Marwanza, head of the mining department in Trisakti University. Greetings to all. First of all, thanks to Allah SWT who always given health, blessing, and salvation for all of us, so that we can be here without trouble at all. It gives me tremendous confidence to be presenting the welcome speech at today's 7th webinar series. Before we begin this webinar, I would like to express my heartfelt gratitude to all of you who sincerely committed to making this event a success. This event would have been possible without the support of each and everyone present here. Thank you, especially to Mr. Heri Purwanto, as the chairman of the Trisakti Mining Engineering Alumni, as well as the initiator of this webinar, Pak Sandi as the moderator of the webinar, and also Ms. Mixindo Kora and Mr. Yuga Maulana, as well as to our lecturers, alumni, and students who helped realize this event. I also thanks to the presenter of the 7th webinar series, who have been pleased to share his knowledge with all of us. Thanks and best regard to Mr. Mathijs Mol. Mr. Matt, Pak Matt is the mining engineer at CMOC Noerthparkes Mine, New South Wales, Australia, which is one of the topmost mining companies in Australia. Webinar is organized and conducted for the students, lecturers, and the general public to gain insight and information that would remain effective in their life and future work in the mining industry. The topic for discussion for today's webinar was chosen keeping in mind the interests of mining students in Indonesia, especially Trisakti University. Closing the speech, I hope everyone is aware of the material that will be presented in this webinar. We are happy to have you all. I look forward to much such webinars involving more people and at higher level. I ensure the webinar will be profitable and fruitful for everyone present here. In closing, I open this webinar. Wish you a great success in your pursuit of. Thank you very much. Thank you, Pak Yuga.
Okay, thank you very much, Pak Irfan Marwanza, for this opening speech, this webinar. So before I give the moderator a chance to lead this webinar, I will read our CV, our moderator CV. So his full name is Sandi Firmanul Haq. He was finishing the Bachelor of Engineering in Mining at the Trisakti University in 2012. So he continued his work as junior mining engineer in Indo Energy Alam Resources in 2012. In 2012 to 2014, he worked as engineering geotechnical the OZ mine in the Freeport, Indonesia. Next, in 2014 to 2018, his position is a chief engineering geotechnical DOZ and the MLZ mine in the Freeport, Indonesia. And in 2018 to 2019, his position is superintendent caving stability in the Freeport, Indonesia. And now, and the 2020 till the 2021, he continued his master program, Master of Professional Engineering in Mining in University of Western Australia, and do the complete course in November 2021, hopefully. So I think this is his CV. To shorten the time, please, Mr. Sandi, to lead this webinar. Please, sir. Thank you.
Okay, thank you, Yuga, for such kind of introductions. First of all, I would say thank you for Pak Irfan, Pak Heri, also Mathijs for his times. Selamat siang. Good afternoon, everyone. Thank you for joining this Trisakti Mining Webinars. So to shorten the time, first of all, I would like to introduce our speaker for today. Our speaker is a mine planning engineer at SMOC Noerthparkes Mine in New South Wales, Australia, who is responsible for early mine studies, including design until financial models, including using UCBC to perform these works. Before joining the Noerthparkes Mines, he has an outstanding experiences in Rio Tinto's caving operations, including designing, developing, and implementation of the CAVE-CAD programs globally for the Rio Tinto's caving operation, including Argyle in Australia, and then Oyu Tolgoi in Mongolia. For whom that didn't know what is a CAVE-CAD is a standardized cave management system for Rio Tinto's caving operations, which is also the topic of his Master of Science thesis at Delft University, Netherlands, which is this program associated with a great European university, including Camborne School of Mine at UK, Helsinki University of Technology, Finland, and then Rheinisch Westfälische Technische Hochschule, Germany. And yeah, he has an outstanding long career in the caving operations. He's also spent a year as a ministry trainee at the Acacia Ridge Presbyterian Church, Brisbane, Australia. Here to discuss PCBC and its application for block caving, mining, and geotechnical data management systems, please welcome Mathijs Mol. Please, Matt, time's yours.
Yeah, thank you so much, all. Yeah, really, really happy to be here. Let me try and share my screen. Are you able to see this, Sandy, or not yet?
Yeah, I'm able to see it clearly. Yeah.
The presentation?
Yep, it's already in the presentation mode.
Yeah, no, awesome. No, thank you so much. Yeah, well, I guess we're covering two topics today. Yeah, so the first one is planning a block cave, and then the second one around the geotechnical data management system. My colleagues were quick to point out that I'm not a guru. I'm not an expert at these things, but yeah, I'm very confident, you know, in the material that I'll be presenting to you, yeah, in the next hour or so. So, I guess the contents of what we'll be discussing today. So we'll cover a little bit around just block caving in general. And then moving on to the first topic, we'll then stop and I'll hand it back to Sandy then for some discussion time after the first topic. And then we'll go back onto the second topic and finishing that off with some more discussion time. So yeah, I'd be keen to get some questions during discussion time. And yeah, there's a lot of experience, I think, in this virtual room. So if I don't know the answers, I'm sure Sandy and Harry and others will be able to chip in to get some more clarity on some of these things. So yeah, a lot of you, I think, know Harry. So we've yeah, spent a number of years with Harry at Argyle, and yeah, I guess over the years I've worked with quite a few different Indonesian engineers, geotechnical engineers, mining engineers, hydrogeologists. Our technical services manager was an Indonesian engineer, and I've always found them, yeah, very warm, very humble people, but with a lot of humor, but always with a wealth of experience. So I guess Freeport is an amazing, yeah, place to pick up so many different skills for underground mining. So we'll move into just block caving. A lot of you will already know this, but it's an underground mining method that generally divided, I guess, in three sort of categories: naturally supported, artificially supported, and unsupported. And block caving sits in that third category, where it's unsupported. And the whole concept of it is that it will cave through to the surface. So it's suitable for mass deposits. It's got low operating costs, and therefore it's able to be mined, you know, having lower grades. It's able to yeah, have very high production rates. So although that's not, you don't necessarily have to have that. I think Argyle was always aiming for around 20,000 tons a day. At Noerthparkes, we've got a similar production rate. But yeah, for example, the Grasberg complex is much higher. Oyu Tolgoi in Mongolia is aiming towards, you know, up from 80,000 tons a day. So it's a lot of tons a day. It's a significant investment, though. So yes, it's low operating costs, but very high investment. So as I understand it, Chiquicamata in Chile is working towards block caving, but it requires around a $5 billion investment. And Oyu Tolgoi, it's similar amounts. So just looking at the image for a few seconds, at the bottom, there's the production level. So here, the ore is available to be drawn. On this level, the loaders will generally run from the draw points. through to either the crusher or some sort of ore pass where the material can move down to the haulage level. The drawbells is really the funnel that connects the production level to the undercut, and the undercut happens initially. It's really just taking a slice from below the ore body, where it will initiate the whole caving process. So once you take that slice, the concept is that the gravitational forces will do its job and will bring the material down into the funnels onto your production level. So just a very typical example of a draw point or a drawbell where the ore is available for mining. Couple of examples. I've seen some of the topics come past, for the previous couple of webinars, and I believe you've seen a fair bit already from Grasberg operation. I'm at Noerthparkes. We were the first to implement this mining method in Australia. The image is showing some of the Noerthparkes caves. So it started with E26 lift 1. They've then had a lift 2, a lift 2 north. E48 is the cave that is currently still in operation on the right-hand side. And that we're at the moment almost finished building another cave, which is lift E26 lift 1 north. And they really, although it's not as common as stoping or anything, it's quite a niche mining method. It really is worldwide applied. So just a couple of examples here: Palabora in South Africa, New Afton, Canada, Henderson in the US. They were going for a long time. There's Codelco, plenty of mine site, plenty of block caves in Chile, and then Oyu Tolgoi. They were supposed to be undercutting already, but they're still planning for that next year. But that's going to be a very large operation as well if it all goes ahead. There's others that currently in sort of the study phase. This Resolution Copper project in the US, very large operation as well, but very early on. So really just at project stage at this point. So let's get into the first topic. Here we'll just cover briefly, okay, what is PCBC? We'll first look at the footprint depth then. Once you have the footprint depth, you want to work out the horizontal aspect, so the dimensions of the footprint. And then as the last, I guess to finish that off, the production aspect and the financial model. So PCBC is used by virtually all the block caves in the world. It does have some competition, but really it is the accepted tool in the industry to plan a block cave and to work out the tons and the grades from your deposit. So it provides evaluation tools to locate the best footprint. And we'll cover that as sort of the very next slide. It provides a tons and a grade schedule, and often that might be a yearly or a monthly plan, but it also then has daily cave management tools. So it's really, it breaks down that monthly plan, works it out into a daily, quite a smart sort of daily tool to manage your production. And then, it's got reconciliation tools as well. So the whole idea of, okay, what were you hoping to get, and what are you actually seeing, once mining has started. So the first is really, once you have a block model, the first thing you want to look at is okay, where, at what height or at what depth am I going to place my footprint? So on the left-hand side, it's just, I guess, an example of what a footprint might look like. So the footprint is really the production level. And this is just, I guess, a typical example of what that might look like. Again, you've got your draw points that basically sit on that footprint, and then I guess a typical underground loader that will move that material on that production level. So I think all of you will have done some work with block models. I guess a typical block model will include your specific gravity or your density, tons, volume per block, and then the various metal grades and your rock type. So in our case, we're dealing with copper, gold, and silver grades, but this could be diamond grade or whatever else it might be. Then the bit of functionality that works out the footprint depth is called the footprint finder. So what PCBC needs here is really everything is based around that block model, and but furthermore it needs I guess the copper price, gold price, silver price, etc., and then also the development cost, mining cost, and then some sort of constraint of so many tons a year, and this might be the constraint might be, okay, the processing plant is able to do 8 million tons a year, and so that's where you're gonna I guess constrain your tons with. Once you've and a lot of assumptions go in this as well. So I guess at Noerthparkes, we've been fortunate enough to have done a few block caves already, and so there's a lot of historical data that can be used. Others are less fortunate, and we'll have to come up with a whole range of assumptions here. Once you then run the footprint finder, it outputs tons, grades, and revenue per RL, so per depth, and these might be 20 meter sort of sections going from all the way down from the block model to all the way up, and it sort of produces, I guess, this shape or this geometry where a whole lot of blocks in this block model, there's really not enough grade, and so they're worthless, and then I guess the purple shape, that is where all the grade is, and all of these purple blocks are worth caving, are worth mining. Here we're just putting some sections through this this shape. So the 9160 level, and we'll see that in the next slide as well, but was in our case for this deposit, it was the most economical. So this is about 1140 meters deep, and really gave us the most value. Then going to 9200, 9300, 9400s, you sort of see that shape changing a bit. It becomes smaller. Then on the right hand side, there's 9500, 9600, 9700. And 9800, and you really see it really loses that sort of that tail of the deposit, and it becomes a lot more chunky. The problem, I guess, is in particular, it's not just a financial or an economic exercise. It's very much also a geotechnical exercise. So with this specific deposit, it's in very competent. It's a very competent rock mass, and the 1100 meters, although it is the most valuable, it's quite unlikely that in this scenario it will cave, because it's such a long and thin ore body, and so even though in an ideal world you would place it at that level, it's really not possible, because it simply won't cave due to the geotechnical conditions. So yeah, again, just that at the bottom of this chart, there's the RL, so the depth of the ore body. The blue line is the tons that are able to be mined from that level, and then the orange line is the dollar value. And so ideally you place your footprint at that max dollar value to be able to make the most money out of this deposit. So yeah, unfortunately, you can't always do that, but it's yeah, that footprint finder is able to figure out very quickly where you know, from a financial point of view, your best footprint should really be. The next slide is just a little bit about I guess some ideally you do a whole range of sensitivity analysis around the assumptions you use and then comparing it to the outputs that will come out of that footprint finder. So the horizontal axis is the mining cost. So on the left-hand side, that the input is a lower mining cost, and then moving on to the right, the mining cost increases. So the mining cost is really, okay, how much is it going to cost to mine 1 ton of material? So this will include your your labor cost, your equipment costs, the cost of the processing. How much is it going to cost to process 1 ton of material? And so increasing this mining cost will obviously give you you know, a lower revenue, and that's very obvious looking at the orange line going you know, going down. So the revenue is going down, and the tons that you're able to mine positively is going down as well. And so yeah, ideally there's a whole range of assumptions you want to do some sensitivity analysis on to get a really decent case together. So once you've done that work, once you've figured out a level that you're you know, you're happy with, that's gonna at this stage in the process is gonna make money, but is also going to cave likely, I guess the next step is working out how big is that footprint going to be. So again, it depends on the area of the valuable blocks. So where is the grade? And then also, again, you have to deal with the geotechnical constraints. So just an example then here, the very dark blue is where the area doesn't make any money. Then moving sort of into that more colorful image, the light blue, the green, the yellow, and the red, that's the area that's going to make money. So the red being, you know, a very high grade area. So in an ideal world, again, you would put the footprint over all these areas. The problem is, I guess, that in the north, it's really quite an awkward shape. Again, it's too narrow, and it will very likely just arch up, and it won't cave that material. In the south, there's that weird little corner that sort of goes into the deposit of all these blue draw points that you know, are not going to make money. But geotechnically, that doesn't make sense. It's asking for trouble, I guess. And so there's on the right hand side, it is that roughly that same shape, but it's just taking off that very narrow area in the top. So you are going to lose on some of you're going to lose some of your gray there, but and in the south we've actually including that little corner of waste material just so that that shape is much more easy to cave. So that's then this is, I guess they call it the best height of draw, which is really that shape, and then adding that three-dimensional aspect to it. So in our case, we've got a fault that runs over the ore body and really has cut all the grade away, and so it really all of your mining will basically stop at that level. And so I guess it's another element within PCBC called the best height of draw, and it just works out how high can your draw columns be. So I guess just that same image. Okay, we've located how high this footprint should be, and how wide and how long should it be. The bottom image is just I guess a very similar level, just in a 3D. So the green is production level, that gold sort of color is your drawbells, and then it's the undercut level in red. I guess the final aspect to this PCBC work is the production schedule. So the production schedule really takes the block model, mixes all of these grades as it simulates drawing that material down. So as the cave progresses, all of that material is going to come down. It mixes, and will then report through to the draw point. So that's what the production scheduler does, and it then provides tons per month, copper, gold, and grades per month. So you then take all of that information, put it in a financial model. Then I guess there's a bit of work required to figure out, well, what is the capital investment? How much is it going to cost to build this thing? And then your operational expenses. So add that to your financial model, and you'll then be able to work out the project revenue or your net present value. And that is hopefully positive, and hopefully, you're going to be able to take that to the next level of study. So this was really, the guts of what I wanted to talk about on a very broad level. What PCBC is able to do, through these couple of different steps. So I wanted to hand it back to Sandy, just to see for some discussion time. Or
yep, thank you, Matt, for such an interesting topic for this topic one. So for audience who wants to ask questions to Matt, please put your questions on the chat room, or just raise your hands, and then you can ask the question straight away. So, jadi buat teman-teman atau bapak-bapak yang mempunyai pertanyaan ke Pak Matt, bisa menuliskan pertanyaannya di chat room, atau bisa raise hand menggunakan button yang ada di bawah, kemudian bisa menanyakan langsung kepada Pak Matt. Right, Matt, we have the first question here from Harry. So the question is, what is the fundamental of parameter for the, I believe FF is the fracture frequency for PCBC to run?
I think that he's probably referring to the footprint finder.
Okay.
I'd say so the parameters on what the footprint finder is based on, I think Harry's asking, right?
Yeah.
Yeah, there's a whole lot of parameters, and really it's been interesting to see that. I guess PCBC comes with a whole lot of default values, and so you know, there's some of the more straightforward parameters would probably be, you know, your mining costs, the development costs, and the draw point. I think there's like a draw point construction cost as well, and so all of these will be very very different depending on the country, I guess, you're operating in. But there's a whole lot of geotechnical parameters as well, and they're very difficult to calibrate. And I guess that's where the reconciliation tool comes in, because ideally, you know, there is already an operating block cave, and you've been able to, I guess, adjust some of these parameters. But a lot of that we simply leave as default, because it's a pretty good estimate as you know, as your initial parameters. So yeah, this is, I guess, stuff like you know, mixing horizon, yeah, how much material is frozen initially, how much mixes vertically, how much is there horizontal mixing going on, and yeah, so unless you've been able to reconcile some of this material on another cave, I think a lot of people in the industry just leave them as default.
All right. Thank you for your answer, Matt. So we have a couple of questions here in the chat room. Another two from Yasir from Ita Surabaya. He asked about is the PCBC as a strategic or a technical schedule? I think he's going to ask about PCBC. Is the PCBC used to for strategic and technical scheduling as well? And then second question is, could block cave mining to mine selective from highest grade to lowest grade, like an open pit mine?
Yeah, let's pick up the second question first. Thank you for that. To some extent, there is some space and room to do that. So depending on how you draw the material, you're able to get to the higher grade quicker. So there's that element of say the high grade is up in the north. You could draw that side of the cave, you know, harder than the southern end. Using that example, you might also want to start undercutting and start your drawbells on the northern end to get that higher grade first. So yeah, it's so to some extent you can do, but in the other end, there's a lot of mixing going on as well, and there's a whole lot of geotechnical constraints as well that will, I guess, not allow you to go that hard, you know, for the higher grade material. So yeah, I guess to some extent you can, but it's not, you know, not at all like open cut mining. And the yeah, I'm not sure with that first question, I guess, strategic versus technical. I guess I've just used it as yeah, very much, you know, trying to figure out where to place, whether the next ore deposit is going to be able to be mined, using block caving.
Yeah. I hope the answers your questions, Yasir. So we have another question here from Suhaila. He asked about in block cave planning, can the production profits be predicted from the certain patterns in the footprints?
I'm not sure if I completely understand that question.
I think here she asked the questions about if we have the different grades in the footprint, can we select which areas should we mine first, like a selective mine?
Yeah, I think you can. I think we're experiencing that at the E48, for example, at the moment, where some draw points are running out of grade. So we've definitely got a number of years still to mine, but some areas will have much higher grades than others, and some of it is running out of grade. And so you can be very selective. So for example, we're simply stopping drawing some of the draw points that don't have grade, so that with draw control there is a lot you can do.
Okay. For that Matt, drawing and stop drawing, is there an implication for doing that, for instance, for economical or geotechnical, for let's say stop drawing here and then keep drawing here?
Yeah. No, I think and Harry will be able to vouch for this. At Argyle, for example, we had quite strict draw control because we saw so much movement on the extraction level, and so we would try and draw the material in such a way that it would relieve the stress on the pillars, and so ideally, if your ground is not very strong, if your rock mass is not very competent, you have to be very careful with stopping some draw points, because it will just the material will just sit on there, it will weigh, and eventually your pillars are probably going to crack up. At Noerthparkes, what we see at the moment is that the rock mass is quite competent, so we're able to get away with not drawing some draw points. But it's very much a balance, isn't it?
Yeah.
And it's to some sense only experience can teach you what you can get away with and what not.
All right. We have another two here. I think this is the last question for the first topic. Just from Bayu, what are the advantages and disadvantages for using PCBC for mine planning?
Yeah, I think the advantage, or at least the fact, is that it's, I guess, the accepted product people use to estimate their their block cave. So there are other flow models, or I guess packages that do similar things. It's just not as accepted yet. If that makes sense. So yeah, there's, I guess, different things available. Itasca does a lot of flow modeling. There's Rebop. We've been using back engineering, and so a lot of these are also able to predict grade and tons, over time. I think it's great for sanity checking, but
Yep.
I guess to some extent, yeah, I guess it's the go-to package at the moment.
Yeah.
Sorry,
Thank you.
Having said that, disadvantages is PCBC is not an iPhone. It's quite difficult to fully understand what the different elements in PCBC do. So perhaps it just takes a while to get your head around, to learn the software, to figure out what it exactly does. So yeah, that's probably the only thing I can mention from experience, I guess.
No worries, mate. We have a question here from William. Hello, William.
Hi, Pak. Thank you, Pak Sandi.
Yeah.
Hi, Matt. I'm William from Trisakti. I have a bit questions related to your experience, actually, Matt. Really interesting when you share. Thank you for sharing this one. Basically, my question is, would you mind to share related to when you run the Noerthparkes second lift, what is PCBC looks like, and telling you about the cave initiation aspect of the, and how that's performed with the actual interactions on that block cave when you run with the two lift mining and Noerthparkes.
Yeah, no, thank you for the question. I don't have, I guess, personal experience with that work. So I probably can't speak from that. I do know that it was difficult. So basically the cave stalled. Sorry, it didn't stall. It necked. I guess it necked into the lift above it, and so a whole lot of ore was sterilized, and they couldn't, they weren't able to get this material down, and so I guess, yeah, PCBC is only as good as the assumptions used, and so yeah, I'm sure they would have done all the work that they planned for a certain reserve recovery, and they didn't get that. So yeah, again, I guess I haven't done the work on it. I'm doing I guess a project at the moment where we're looking at a deposit that is adjacent to an existing cave, and so yeah, it's very interesting, I guess, how a new cave is going to interact with the cave that is next to it or under it. I think the challenge will probably be in the flow modeling, and the caveability analysis. Perhaps not as much in the PCBC aspect of it.
All right. Okay. So basically, with that case, you are still using PCBC to tell you that is still have a revenue with the good revenue, something like that, or you have other tools to tell you for some mining engineering.
Yeah, no, you're right, William. Yeah, we for a lot of the tons and the grade schedule and the mixing side of things, yeah, we do use PCBC for that, but at the same time, for the The capability analysis, we use yeah, a consultant at the moment to do that work.
Thank you for sharing that one. Thanks, Mas Andi.
Thanks, William, for such interesting questions about the cave interactions and cave stall. We have last question from the chat room here from Muhammad Raihan. He asked about, do we as mine planning engineers adjust the mine planning or a PCBC model based on the price change, or also revenue also change, so it's the profit also change?
Yeah, no, that's exactly right. Just again, working on a deposit here, and it's there's a lot of tons. It's a very big deposit, but the grade is not very high, and so what it looks like at the moment is that we simply have to wait until we mine this deposit until the copper price has gone high enough, increased enough to be able to afford the investment and the operating costs, etc. So yeah, no, you're definitely right. Like PCBC is very much able to work with that and rerun these scenarios very easily, very quickly. And that's, I guess, where the sensitivity analysis comes in. Say you might want to mine a deposit, but it's probably only going to be ready in 5 years' time. What is the copper price then going to be? And you might want to, try and set a number of them and then run different scenarios.
Yeah, regarding to that question, also, Matt, when you do like a financial modeling, like say in the feasibility studies, I believe that PCBC can run the optimization to give us what is the best scenario. Was that including the rates of dilutions of different height of draw to acquire that, let's say, the best NPV that we will have?
Yeah, no, that's right. It's another parameter that that you estimate. So I think, for example, the default parameter for that is 60% into your draw column. You're going to be seeing dilution, and if your draw control is very good, this might be true. If it is perhaps not so good, you could see dilution a whole lot quicker, and so yeah, it's a huge consideration, isn't it?
Yeah, including one of the question I have here, because my experience as a geotechnical engineers, we have like a cave rates, right? From PCBC, do we have a in the early stage? I know we need to put the geotechnical considerations into the planning, but based on the grades that we have and the dilution that we have, is the cave rates also dictate from this automatic optimization from the PCBC?
No, not really. It's really the geotechnical engineer that has to work that out, and then it's more a parameter that you will put into the system as opposed to getting the parameter out of the system.
Okay. All right. So we don't have any more questions from the chat room. From the audience, is there any more question for topic 1. We still have 3 minutes here to continue the topic 2. All right, no, so we can continue to topic 2, Matt.
Yeah, thanks so much. Yeah, thanks so much for the questions. I'll see. Yeah, you can still see this.
Yep.
Yeah. So yeah, we'll move on to topic 2, which is around geotechnical data management systems. We're going to just look at what is it? Why is it important? What's the problem? Is there even a problem? We're looking at a solution, some of the lessons learned, mostly the hard way for me, and then just some output examples. So what is it? What is a geotechnical data management system? So there's really, I guess, sort of four, at least 4 components. So the first one, it has to log and be able to import data, ideally automatic. And there's been so much movement, I guess, in this space for the last 10 years, or at least since I've been I guess working with some of these things. So an example is extensometer data. 10 years ago, I would visit a mine. Someone would, a technician and often an engineer would go underground. They would walk the whole production level and stop at every extensometer station. So an extensometer measures the rock mass movement, within the rock mass. And so the technician would have a little reader. They'd connect it up to the instrument. On their reader, they'd see 5 or 6 readings. The technician would then, write this up, and so do all of the extensometer's instrument on the production level. He'd go back up and then enter it into Excel. Within that Excel file, the geotechnical engineers would have built some sort of analysis, and that's how they, would look at the data. But it was very involved. It takes so much time. And when you now go to the same place, the extensometer is, connected up automatically. It sends the data to the surface. It's stored properly. It's analyzed automatically. And depending on how you set the thing, it will read data every single minute. And so, there's been a huge change over the last little while, I guess, for this data logging and data importing. But it's key to having a good geotechnical data management system, that it will allow, ideally this automatic data recording. So the second thing that's critical, it has to be able to store, maintain, and process data in a secured central database. It's historically, it has not been great. Data gets stored in an Excel file, Access databases, and it's all over the place. But really, it needs to be maintained properly, by the IS&T team on site. It has to be secured. So, you want some people to see your data, and other people, so you really don't want to have, allow viewing your data. So the third thing, it imposes a reporting regime. And the data is only data, but really you want your data to be information. So often a whole lot of investment, a whole lot of effort goes into collecting data, but ideally you want to be able to see this data in a well-presented shape, be able to send this data out automatically, and it needs to it needs to be done in a well well-organized manner. So a geotechnical data management system will allow that. It won't then depend on the one engineer. If he has time, he's gonna do up that report, send it out. But ideally, these things happen automatically. The fourth, it provides an auditing regime. And we've seen, I guess, so often that data, when it's not stored properly, calculations that are sort of behind the report, they change. Simple errors creep into Excel files. The problem, and often an engineer might actually know what he's doing at the time, but a year later, no one remembers. Where is the data? Why did we change this calculation? Why did we change these parameters? And so being able to track when data or when calculations change is really critical. In particular, when something happens, you might have an incident, and you need to be able to go back to the data and see what has been done to the data. And so, auditing is very important for that. So we're sort of taking a step back here. So a geotechnical data management system is important. And so it stores and processes a lot of geotechnical monitoring data, but why do we do geotechnical monitoring? In particular here for a block cave. So there's really 4 critical areas. And the first one is we do geotechnical monitoring to check the initiation and the development of caving. So once the undercut comes through, the idea is that the cave will start growing from there. But it's important to figure out where is it growing, how quick is it growing, how is it growing compared to how much we're drawing. So this illustration is showing, at the bottom, that's the material that has fallen down from the cave back. Then there's a little air gap, and then there's the cave back. And so I don't know if you can read this, but it talks about a zone of loosening. So that is the area where the rocks will start separating from the cave back. And so being able to track what is happening there, it is very important. When William asked that question, we sort of talked about, lift 1 and lift 2, and how lift 2 had moved into sort of quite a neck position instead of having the cave vertical. So being able to track and see what is actually happening with the cave is not only important from a safety aspect, but also from a resource recovery aspect. We plan to mine this area, this deposit, but are we actually getting it? Is the cave moving there? Then the second one is to check the stability of the extraction level installations and other mine infrastructure. So it's, I guess a block cave is quite interesting. So you want the material to be weak enough so that it caves, but you want it to be strong enough to keep the tunnels open. So there's there's I guess a balance, and so your production level, your extraction level or your haulage level are critically important to remain stable. And so this is just an example of where the material, where the ground support has not been able to support the tunnel. So you see here how some of the ground support is giving way, and so really it's geotechnical monitoring that is able to pick this up, and it's critically important not only for the production because your machines need to continue to run through the production level, but obviously for safety of your personnel. And the third one is to monitor the surface subsidence. So this is the top one. Just shows how a block cave has propagated through to the surface and is making this this pit in these fields, and at the bottom it shows the various zones of movement. This is an example of there's actually not much infrastructure, so perhaps this is not very risky to be subsiding, but then very often very close to your block cave you might have the shaft, you might have offices for the mine personnel, there might be your conveyor belts that will move the material through to the processing plant, and so monitoring when you're propagating through to the surface and how far the subsidence is reaching, again, is critically important. And then the fourth one, it monitors the effect of draw control strategies and resulting fragmentation. So we've talked a little bit about a draw control strategy. That it, for example, it helps to relieve the stress on the extraction level. If that's struggling, you're able to play around with that a little bit to try and get some of that higher grade early. But it also impacts the fragmentation. So there's one way to do it that will result in very blocky fragmentation. A lot of struggle might be around hanging up of your draw points, or simply lots of oversized rocks reporting to the draw points and not being able to fit through the crusher. And so again, geotechnical monitoring is the way to figure out, okay, is my draw control strategy, is it effective? And so all of these feed into the safety of your personnel. It also feedbacks on the assumptions used. So with PCBC, we've talked a lot about a whole range of assumptions having to be used for figuring out your schedules. What is what's the geotechnical conditions for this rock mass. And so I guess an example is, so we figured out tons and grades from the draw points. That was our schedule. But what is it actually doing as you've started mine? Are you seeing the grades you expected? If not, well, why not? And so you want to check those assumptions you've put in place, and that then leads into the next thing. You want to be able to predict forwards. So grades is an example. What grades have you seen so far, and what grades are you hoping to see in the future? But it's the same for the rock mass response. If you've seen a lot of, for example, convergence, if you're struggling to keep your tunnels open, you want to be able to figure out, well, what is it going to do in the future, and what do I need to do to change that? So geotechnical monitoring is a very wide topic, and so a geotechnical data management system needs to be able to handle a whole range of different data types. And so I've just listed a couple. I won't go through all of them, and this is only a few. There's many more. Sandy will be able to vouch for that. But so we talked about extensometer a little bit. The open holes give you a good idea on where the cave back is at any one point in time. Production, seismic data. These three are around draw point observation. So You want to know what the geology is, the water content, the fragmentation, and all of that feeds into, for example, major operational hazards. So having a wet draw point with very fine material, it's a huge risk for a mud rush. And so you want to be able to monitor that ideally constantly, but at least, perhaps every couple of days or every week, just to figure out, well, what is the risk rating of these draw points. And so these different things will have to feed into a geotechnical data management system, but they're very different types of data. Your seismic data as opposed to your draw point data. So we're just looking here at a couple of examples. For example, shotcrete cracks on the top. What are these cracks doing? Are they growing? Are they stable? If they're growing, if they're increasing, well, what are we going to do about it? And so you want to be able to record these one way or another. Then the convergence really is just measuring the width of the tunnel. Is that staying the same? Well, that's good. If it's coming in, that's a worry. And so, being able to monitor that and then respond very quickly, helps a lot. So here, just an example of the cave trackers. Harry just told me that is his bread and butter at the moment, working with these cave trackers. So the idea here is that a beacon ends up in the caved zone. When it moves, you're able to pick that up with the detector. And so again, being able to see that data, process it, report it, is just so important, because it it feeds back into so many things. So that's all good and well, but what's the problem? I've just heard people struggling with the same everywhere, and so this is some of the problems. Without a good data management system, often problems include there's no real-time hazard analysis. It often takes time to collect the data, to process it, to analyze it, and it's difficult. Often, at least in the past, geotechnical engineers would spend a whole lot of time collecting the data and wouldn't always have time to analyze it. At least that's what I think we've seen a lot in Australia. The data, we've covered that a little bit. The data often lives in many different places. So a seismic system will often come with a seismic database, a proprietary database, and that will just include the seismic data. Your convergence data might be in an Excel spreadsheet. Production data might be in some sort of PitRam, production system. And so all of these things live in very different areas, and it's very hard to access. Data is often misplaced and contains errors. So over time, data disappears if you don't have it saved, properly. It often includes errors as well. Again, so many Excel analysis, and it's so easy to have mistakes. For whatever reason, engineers are often very stubborn, and so we're great at making our own VBA code, our own macros, and it's very difficult, I guess, looking into the next line as well, that picking up someone else's file is very difficult to troubleshoot. So when it breaks, it's often very difficult to fix. And so changing people and responsibilities, just wanted to mention one example of a mine I visited. The this is a sub-level cave where the managing director had put in a system coding up the whole thing that would take conveyor data, it would take processing plant data, it would take production data, some sort of various monitoring data types. It would bring it all together, and then it would run a whole lot of analysis on it, and then it would send out reports. He built it by himself, and so he moved on into a consulting role. However, the system was so difficult, they would reach out to him every time to come and fix it. So if it broke, they would reach out to him. He'd get in and fix it. If there were updates to, say, the production system, it wouldn't be able to connect to this new system anymore. And so having the right people in place is great if they remain in place, but if they leave, it can cause a whole lot of headache if you don't have something implemented, well designed, well maintained. So lack of good reporting and analysis. If it's not done through a proper system, that reporting and analysis is only going to be as good as the engineer doing it. And often, great things can be done, but say someone new, someone fresh comes in, perhaps not a lot of experience, your reporting might not be great. The last one, inconsistencies from mine to mine. So I'm specifically thinking of a large mining corporation who has several mines, and for a head office, or for people that manage these different sites, it's very very inconvenient to look at sort of similar data, but reported very differently, analyzed very differently. So how can you try and compare these different mine sites if it's not done the same way? An example is draw compliance. Some were calculating the draw compliance in a whole different way than other mines, and it's difficult from when you move from the one mine to the next within the same business to have to learn the whole thing all over again. So this is, I'm saying here, the solution. It's really just a solution. So on the left-hand side, you've got a whole lot of different data types. So yeah, example, tons, grade, seismic data. There'd be different databases, different files. You really want all of these data types, all of this data into the one central database, which sits in the middle, which might be an SQL database or Postgres, anything that can be well maintained, well versioned, well backed up. So to get the data into the central database, there needs to be some sort of extraction, transform, and load layer, an ETL layer, which really just changes the data format, gets and brings it into this central database. A lot of data might need some more calculations, but that can be done through that layer. Then on the right-hand side, there's some sort of user interface through which you'll be able to set up automatic reports. So this might be, like a daily seismic report. It could be, okay, how many tons have we drawn, last night? Things like that. Ad hoc analysis. So that's where you would, always allow your engineers to get in, look at the data, do a whole range of analysis that you wouldn't normally set up as a standard thing. And then again, offsite access. So you could have for example, again, a big mining corporation. You might only have a graduate geotechnical engineer, perhaps, and then if the head office is able to help out, for example, the principal engineer is able to help out and look at the data and mentor a young engineer like that, that's ideal. So then ideally it would have an API, an application programming an interface. And really it just standardizes this all of this data so it can be accessed in exactly the same way every time. On top of that, you would be able to access the data with 3D software. In particular, block caving, it's so important that you view things in 3D and also over time. And then the BI packages have been really good to analyze and set up standard reports. So this might be Tableau or Power BI or different packages. And I'll be quick because I think I've gone over my 25 minutes. I guess some of the lessons learned, in particular the hard way, is I guess you need a vision. You need to be clear what you want to get to, what data to include, what reports you want to see, because it could really go anywhere if you don't have that clear vision. It does include a lot of people. Ideally, you have site IS&T included, geotechnical engineers who will want to see the reports. You have a project manager, software developers if you do it in-house, but otherwise some sort of company that can build this thing for you. This is, I guess you need to figure out whether you want to build this thing in-house or you want to buy it off the shelf, and it's worthwhile doing your research. We're sort of getting back to this in a couple of slides as well. What I've found is when there are off-the-shelf components, for example, these BI, business intelligence packages, like Tableau or Power BI, they have been so good, as opposed to having software developers build their own reports. Go with off-the-shelf components if they're available. The product must handle the concept of time well. Not, for example, 3D packages don't all do well with time, but it's critically important. It's not cheap, it's not quick, but it's extremely beneficial when it's implemented well. So just a couple of examples that ideally you would want to be able to produce from your geotechnical data management system. So some surface subsidence, a whole range of seismic events, drill holes, block mold data, convergence. You want to be able to visualize. So there's just a couple more examples, and if there's specific questions in a minute, we can go back to them, but we'll finish up on the next slide. So there's a couple of systems that are available at the moment that at least are a partial solution to this problem. And Sandy might have worked with Canary, but that's implemented at Freeport. Oyu has had it. I don't know if they still do. GeoExplore, Kennecott in the States uses that. Diavik uses that. Amex Wrap, we have that here on site at Noerthparkes and Acquire. And there's other things like Geoscience Integrator, Maxwell Geosystems, and more. They all do some of these things we've talked about, but I haven't really seen anything that does it all and does it well. So that was so I'll hand it quickly back to Sandy. That was what I was wanting to talk about, the geotechnical data management system.
Thank you so much, Matt. This is the field that sometimes both geotechnical engineers, mine engineers, boss of the boss get headache when they couldn't find reliable data. Some data lost when we not stored the data, appropriately. Especially when we did when we have like the major events, and then we need to do back analysis, and then where's the data? And then why is it different? So yeah, for the audience data, geotechnical data management systems play the significant roles in the all the caving operations, because caving, I think, is not only about production, but everything. Yeah. Okay. So for this topic, we already have a bunch of questions here from Harry. Okay. First question is, database management in underground mining would capture a big amount of data, and not many companies aware of this situation unless major operations. What is the investment return of implement well-designed setup? Is there any ways commissions database management system in relative low cost? And then the last question from him, is there any dollar or production rights or capital spending as a trade-off or trigger where or when we need the geotech management system in place?
Yeah, well, you might have to repeat some of the questions, but I think at least, and Harry will have seen that now at Oyu-Tolgoi, but you're right, like they do generate huge amounts of data, and it's difficult to to be able to process and store the data that's being produced by some of these things. I guess that that they do a scan after every cut, and the 3D scans are huge, and so it is a problem. Like you're right, but it's not unovercomable, I guess. I think the iron ore industry in WA has had real-time autonomous trucks running for a long time now, and the amount of data that is being generated is huge as well. And but you're right, like it is expensive, and it is a lot of work. But I think the beauty is that, for example, at OT, they pay the contractor on how well they've fired a cut. So if it's over a certain overbreak, they will lose their bonus, and if it's within the range, they will get bonuses for their development meters. And so it really does. It's very hard, I think, to put a value on it, but it does show, I guess, how critically important it is. Some of that data capturing. If that directly influences how much the contractor is getting paid, and so I think it is. I think it's difficult to put a value on it, but at the same time, it's it saves. It's able to assist in saving lives, because you do manage for example your mud rush risk through it, your air blast management, and does that answer some of the question, Harry?
Yeah, Matthias. Yeah, thanks so much. I got your point. Yeah, I think one of the biggest thing and the fundamental thing is the data, send us some condition that we need to quickly make a decision. Right? I think that wouldn't be any dollar worth to saving mining personnel undergrounds working in the safe condition. Thanks, mate.
Yeah, no, thank you.
Yeah, thank you, Harry. Yeah, it is difficult to find what is the money to put for the such a you know, monitoring systems, data management systems from the beginning of the block caving. And then this the second question from Nazri. He asking specifically about the monitoring of surface subsidence, but it's related to Grasberg, but it's a general in the for block caving that will create the subsidence. He asked about how to control the collapse with the geotechnical data. Probably he said how to control the propagations of the surface subsidence.
Yeah, I think I'd say your primary the primary way you would control some of it, I'd say, would be the way you draw the caves. So your draw control strategy. I think one example of what we've seen is that at some point there were issues. We were seeing the pillars fail. Lots of convergence in some areas, and so there was a high. The idea was that if you draw that area directly around it quite hard, it would relieve some of the stress, some of the pressure on the pillars. And so that was done for some time, but the cave actually propagated through to the surface almost directly above that area that was drawn quite hard. And so that was probably not ideal, because I guess the surface subsidence was quite sort of a small area initially. And I think overall, it makes much more sense to draw the cave more evenly, so that the whole ore body will move down sort of at the same time. And so that there's some elements that you can do with draw strategy, but really you're dependent on the rock mass, the geotechnical conditions that are in place. So, for example, a lot of block caves are situated under an open cut mine, and so a lot of the surface subsidence will just go, happen directly up through in the open pit, and so you will see a lot of movement in the pit. Benches failing, and but it could then move outside of that as well. But really, it is the rock mass that's in place.
Yeah, but in addition to that, to answer the question from Nazri, basically consultants like Beck Engineering can model the frac propagations based on the geotechnical inputs, and then like Matt says, the draw strategy, what is the cave rates, and then what is the rock mass of some block, and then how it will propagate over the times of mining. I hope that answers your questions, Nazri. And then next questions is from Briam Fancesa. So Briam asked about whether is there any method to monitor the fragmentations before it reaches the draw points. Like how big is it before it's to monitor, to prevent from hang up?
And that's probably not my expertise, and this might be more you, Sandy. But I think, for example, the work what we're doing now on a certain deposit is where the drilling will will tell what the fragmentation is very likely going to be. Is it very blocky? How many fractures are that per meter? I guess there's a whole lot of geotechnical drilling that happens to figure out what kind of rock mass are we dealing with? Is it very fractured, or is it very blocky, very competent? yeah.
Yeah. So I think in addition to that question, to answer Brian questions, is the method to monitor the fragmentations inside the cave itself is very difficult, because there is the empirical approach to monitors what is the average rock fragmentations in the draw points of different height of draw. That's the only way to monitor what is the size of the fragmentations visually, using the visual observations. But yeah, there is to control, in terms of to control the fragmentation, I believe it's starting from the rock mass estimation, how the rocks, what is the rock fracture fragmentation frequency of the rock mass to create the acceptable rock fragmentations in the draw points. Yeah, I hope that's answer your questions, Brian. Yeah, we still have here 12 minutes, I believe, before the closings. So if audience will ask question either from the chat room or in personal, please ask your questions. Jadi kalau teman-teman mau menanyakan mengenai Geotechnical Data Management System, silakan aja tanya. Kalau mau tanya pakai bahasa Indonesia juga nggak apa-apa, tanyakan saja. Nanti saya bantu untuk translate ke Mathijs. Mau tulis lewat mau tulis menggunakan bahasa Indonesia melalui chat room, silakan. Mau tanyakan langsung pun silakan. Ini kesempatan yang baik buat nanya seputar dua topik ini. So while waiting the audience asking some questions, Matt, probably I'll ask in your experience in the Noerthparkes, are you like is the geotechnical team and the mine planning or cave management team in one divisions or stuff? So you need so that's why you can compile the data easily.
Yeah. I guess we're quite a small team. I guess there's sort of a technical services department, and there's a life of mine planning team, and so the life of mine planning team is, I guess, the smaller one. So we've got 2 mining engineers and then a geotechnical engineer, a couple of senior mining engineers, and then the technical services. Yeah, looks a little bit like that. It's a bit bigger, but yeah. Even just working on the PCBC side of things, yeah, we're in constant communication, I guess, with the geotechs, because yeah, I guess it is so critically linked, isn't it?
Yeah. That's right, mate. So yeah, because like you said before in the slide number, sorry, what is it, number 32, that's it's a lot of data need to be processed and then to display to the and then this report need to be in a good package, like the to hit or to be understandable to the audience that he wants to, sometimes it's quite tricky because the higher levels wants this exact reports, to them to understand, easy to understand, you know.
Yeah, no, that's right. Yeah, there's always a couple of layers of reporting, isn't it? Whereas you know, the manager Geotech might be keen to see quite a lot of detail in the data, whilst I guess you know, some sort of general manager will probably only want to see you know, is it safe, or is it, you know, not safe, etc.
Yeah. And then probably can you show the slide number 34 or 35, I believe. Yeah.
I don't. Do I have?
Yeah. Go down. Go up. Yeah, this one.
This
Probably
guy?
Probably the audience want to know that is this produced by like one process, or using different software to produce the report like this?
Yeah, this is quite an old I guess slide. So the right hand side, we went down the track of connecting and doing a whole lot of work with the GoCAD mining suite. So that would then connect to a database, being able to pull up a whole lot of different data types, and so yeah, so all of that, I guess, is within the GoCAD mining suite here, and then on the left, yeah, so that was it's showing the, I guess, the you know how we were talking about the draw point observations. Just shows the I think the fragmentation here, it's a bit small. Yeah,
I think it's fragmentation. Yeah, different fragmentation pie chart, I think.
Yeah.
Oke, teman-teman, Bapak Ibu, jika ada yang masih kurang atau masih mau menanyakan ke Pak Matt terkait presentasi ini, kami persilahkan. Jika tidak ada, maka saya akan serahkan kepada MC. Alright, Matt, I think there's no more questions from the audience here. We finished right on time. Thank you for such a great presentations, and yeah, this is such a great opportunity for students in Indonesia, and professional also, and the audience to interact and share knowledge with you, and then ask some questions about the importance of mine planning using PCBC, and especially the critical things of the geotechnical data management system. Thank you very much. And then I'll hand it back to Yoga. Please, Yoga.
Okay, thank you, Mr. Sandi. Okay, before we close this webinar session, allow us to take photos or documentation of this session in the room Zoom. Please, all participants can turn on the camera for we want to take the documentary for this webinar. And please fill out the attendance list. We have sent the link in the chat column. Okay, maybe committee can help. Habibah, bisa tolong Ababa ya untuk foto bersama.
Kalau kirim makanan ke tempat yang SS ya Pak, mulai dari slide pertama. Selanjutnya slide kedua. Selanjutnya slide ketiga. Sudah Pak.
Okay, thank you, Habibah, for the commentary. So we are at the end of this webinar. Once again, thank you very much to the speakers, Mr. Mathijs Mol, and the moderators, Mr. Sandi Permanohak, for taking your times for this webinar. And thank you to all participants for joining today. Hopefully, we are always in a good health, and see you in the next Trisakti Mining Webinar. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Matthias.
Thank you very much.
Thanks.
Thank you, Harry.
Matt.
Thank you. Enjoy your weekend.
Enjoy Mongol.
Thank you, guys. Thank you so much.